Hello my dear students. In our previous class, we have learnt about the expression for the capacitors connected in series. In today's class, we will learn about effective capacitance of two capacitors connected in parallel. When the two capacitors were connected in series, that is end to end, the potential difference across it was not same. It was different. V1 and V2. What was same? The charge stored in both the capacitors was same, that is Q. Now, when the capacitors are connected in parallel, the charge stored in the two capacitors are different, but the potential difference across the two capacitors are same. So, let us consider the two capacitors connected in parallel. Parallel means they should be connected end to end. The two terminals should be connected end to end. Then we have to connect it across a battery of potential difference V. When it is connected to a battery, these capacitors will get charged. So what we are going to do here, let us consider two capacitors of the capacitance C1 and C2. Let V be the potential difference across the capacitors. So here also V, here also potential difference is V. Let Q1 be the charge stored in this capacitor C1 and Q2 be the charge stored in the capacitor C2. So I can say here plus Q1 and here minus Q1, here plus Q2 and here minus Q2 charge is stored across the plates. Correct? Okay. So let us consider, we have considered two capacitors of capacitance C1 and C2 connected in parallel with the potential difference V. Let Q1 and Q2 be the charge stored across the capacitors. So we can say Q1 is equal to C1 into V, because Q is equal to CV. And also I can say Q2 is equal to C2 into V. Let us mark it as equation number 1 and 2. Then the net charge stored across the combination of the capacitors is Q is equal to Q1 plus Q2. Substitute 1 and 2 in above. So what do we get? Q is equal to C1V plus C2V. V is common, so C1 plus C2 into V is equal to Q. Let it be equation number A. Now, instead of two capacitors, let us take one single capacitor which is equivalent to two capacitors capacitance. So, let us replace the two capacitors by a single capacitor of equivalent capacitance CP. And we will place it across the same potential difference V. Let the charge stored be Q. Plus a Q minus Q across the plate. Therefore, total charge stored is Q across the capacitor. Then I can say Q is equal to, for this one I can say Q is equal to CP into V. Let it be equation number B. That is, instead of two capacitors, we are placing only one capacitor of equivalent capacitance CP. And we are placing it under same potential difference V. So from A and B, equation A and B, we can say that CPV is equal to C1 plus C2 into V. VV gets cancelled. So CP is equal to C1 plus C2. This is for the two capacitors when it is connected in parallel. If there are n number of capacitors connected in a parallel, then I can say Cp is equal to C1 plus C2 plus C3, etc. up to Cn. If there are n number of capacitors. In general, we are speaking about. So, what we have done, let us consider two capacitors of capacitance C1 and C2 connected in parallel. Therefore, potential difference across the two capacitors is same, that is V. Let Q1 be the charge stored in the first capacitor and Q2 be the charge stored in the second capacitor. Then I can write Q1 is equal to C1V and Q2 is equal to C2V. Therefore, I can say Q is equal to Q1 plus Q2. Let us substitute. That is what? This is a combination of the two total charge or net charge stored in the combination of the two capacitors is Q is equal to Q1 plus Q2. So therefore I can write Q is equal to C1V plus C2V. See, V is common, take it outside, so there is remaining. We will replace these two capacitors by a single equivalent capacitor of capacitance Cp, and the potential difference will maintain it as same, that is V. Then the charge stored across the capacitor is Q. Therefore, I can say Q is equal to CpV or Q is equal to CpV. We will see here. Equation A and B are almost, they are equal. Q and Q are equal. Therefore, from equation 1 and 2, A and B, we can say CpV is equal to C1 plus C2 into V. V gets cancelled. The remaining is Cp is equal to C1 plus C2 for, this is nothing but effective capacitance of two capacitors connected in parallel. If instead of the two capacitor, if there are n number of capacitors connected, then we can write Cp is equal to C1 plus C2 plus C3, etc. up to Cn. Understood? See, this derivation and previous derivation is very important for your final exam for 5 marks. Either they can ask anyone from these two derivations, or they may ask problems related to these two relation. That is series and parallel for 5 marks. Understood? Very important concept. Next, we are going to find out the expression for energy stored in a charged capacitor. Expression for energy stored in a charged capacitor. This is also one of the important questions. Once it has come in the final exam of 2017 and 2016 question paper for 3 marks. This is 3 marks derivation. Okay. That is energy expression for the energy stored in a charged capacitor. To find out this expression, we have to consider a capacitor. Okay. Let us consider a capacitor. Let its capacitance be C. Let us consider a capacitor of capacitance C. Okay. When we draw a capacitor, 2 terminals should be there. Okay. We have considered 2 capacitors. If when it is connected to a battery, it is getting charged. Correct? So I have said in earlier case, when you connect it across the battery, it starts charging. As your cell phone itself, when you take a cell phone, if it is not charged, it is not fully charged, you will keep it for charging, correct? When you start connecting it for a charging to a pinhole, if you switch it on, it starts charging. In same way, when I connect the battery for this capacitor, it starts charging. Okay, now it is charging, and it will be fully charged. Let Q be the fully charged when it is completely charged. Okay, so we will consider V be the potential across it when it is fully charged. Okay, now what I will do is, when it is fully charged, okay, fine, it is fully charged. Now total charge is Q, plus Q and minus Q across the plates. We will go to the little bit previous step, that is, now it is not fully charged. It is charging. The process is going on. Charging process is going on. So what I can say, it is an intermediate state. Your mobile is not fully charged now. It is charging. Still the process is going on. I'll call it as intermediate state. During that intermediate state, when the current flows, it will start charging. So the charges always move from lower potential to higher potential region. So always the charge flow from minus to plus, that is lower potential region to higher potential region. Okay, the charge is moving from lower potential to higher potential. Charging is taking place at some intermediate state. At one point, it is not fully charged now, some point. What is the charge? The charge is the present at the plate, let it be Q dash. Here minus Q dash, it will be here, it will be plus Q dash in this place. It is during the intermediate state, the charge in the plates across the capacitors, let it be Q dash. Then I can say Q dash is equal to CV. Now when it is let the potential be V dash. So I can say CV dash. CV dash. At this stage, the potential difference I can say, what is the potential difference we can say? V dash is equal to Q dash by C. So from this I can say, the potential difference at the stage V dash. When it is fully charged, the potential difference is this one, V. Now what we are doing? It is charging now. When it is charging, there is a potential difference across these two plates. That is V dash. So I can say Q dash is equal to CV dash, or V dash is equal to Q dash by C. During this intermediate state, when the charge is moving from lower potential to higher potential, work is done. So the small work done, that it be delta W. In moving the charge Q dash from one plate to another plate for charging is, what is the work done? Work done is nothing but potential into what? Charge, correct? It is nothing but potential into the charge. So to move a small charge Q dash, I'll write delta Q dash from lower potential to higher potential, the small work done is delta W is equal to potential into delta Q dash, where delta is a small charge. To move this small charge from lower potential to higher potential, the work done is delta W is equal to potential at that point, potential difference during that point into the charge. Then I can substitute in the place of V dash as Q dash by C into delta Q dash is equal to delta W. This is the small work done to move this small charge from lower potential region to higher potential region. Instead of that, now I want to make it completely charged, that is full charge. To make it full charge, how much amount of the charges to flow from one region? What is the total work done in moving the charges from lower potential to higher potential? Therefore, total work done, I can say, total work done, we will do it in terms of integration. That is, you are adding up. So, integration, total work done from charging it from 0 to fully charged means how much? Q. Correct? To make it completely charged. From your mobile is not at all charged now. So, 0. Full charged Q. So, therefore, 0 to Q in Q dash by C into, instead of delta, we'll write dq dash for integration. Okay. Now, while doing integration, before doing integration, we will take the constant outside. So, when we take constant outside, it is 1 by C integration from 0 to Q, that is Q dash into dq dash. Okay. Next, how to integrate? Integration of x to the power n is x to the power n plus 1 by n plus 1. X to the power integration, should I write? Okay. Integration of x to the power n is equal to x to the power n plus 1 by n plus 1. Here integration of q dash, that is integration of q dash is w is equal to q dash to the power 1 plus 1, that is 2 by 1 plus 1 is 2, from where to where? 0 to fully charged Q. This is nothing but the limit. Okay. Now, apply the limit. Upper limit minus lower limit. So, Q dash should be written as Q square divided by 2 minus 0. Because 0 square is 0. 0 by 2 is 0. So, 0. Q square by 2 minus 0 is Q square by 2. But one constant was written outside. So, write it here also. So, therefore, we can get it as 1 by 2C into Q square, or W is equal to Q square by 2C. This is the amount of work done in completely charging a capacitor. And this work done is stored as an energy in the capacitor. So I can say expression for the energy stored in a capacitor is U is equal to Q square by 2C. Understood? Very easy it is if you understand. What you have done, let us consider a capacitor of capacitance C. Let us connect it to a battery and make it charge. When it is fully charged, the charge stored is Q. Now, during the intermediate state, let the Q dash amount of charge is moved from lower potential to higher potential. So, the potential across that is V dash at that moment between the plates. So, therefore, I can say V dash is equal to Q dash is equal to CV dash and V dash is equal to Q dash by C. Now, the small work done in moving the small charge delta Q dash from lower potential to higher potential is delta W is equal to V dash into delta Q dash. So, in the place of V dash, substitute the value, we will get delta W is equal to Q dash by C into delta Q dash. That is a small work done. To charge it from 0 to Q, total work done is integration from 0 to Q dash by C into dQ dash is equal to, take the constant outside, this is remaining. Integration of x to the power n is x to the power n plus 1 by n plus 1. This is to the power, it is 1. So 1 plus 1 is 2 divided by 2. Limit from 0 to Q. upper limit minus lower limit. So q square by 2 minus 0. That is q square by 2c. This c is constant which we have taken it here outside. So therefore W is equal to q square by 2c. This work done is stored in the form of a energy in the capacitor. So therefore I can say U is equal to q square by c. Very, very important derivation for 3 marks. See, we can write different expression for energy here because till here only, okay, for the exam. That is not, I'm not saying about the portion. This derivation is still here. Now, see here, we got the expression U is equal to q square by 2c. In the place of q, I can write Vc because q is equal to Vc. I can write Vc square by 2c, then V square C square by 2c. C gets cancelled. Therefore, I can write one more expression for energy stored in a capacitor as U is equal to V square C by 2. One expression was this one. Now, one more expression is this one. Can I write one more expression? Can you help me for one more expression? See here. In the place of C, we will substitute. U is equal to Q square by 2. C is equal to Q by V. Correct? C is equal to Q by V. Then one Q will get cancelled. This will V will go up. So Q V by 2 is nothing but one more expression for energy stored in a charged capacitor. So you can use 1, 2 and 3 expressions for solving problems. While solving problems, you can use these 3 expressions for finding the energy stored in a charged capacitor. Understood? Any doubts? So these are the 3 expressions which you can use for solving the problems. Now, next, while solving the problems, you are having one more, you can use one more question. I mean, one more type of question can be asked. That is, energy stored per unit volume. Energy stored per unit volume. See, we got the expression for the energy stored as U is equal to Q square by 2C. Correct? Sorry. Q square by 2C. We have to write expression for U by V. How can we write? See here. Charge you can write in terms of surface charge density. That is, surface charge density is equal to charge per unit area. Am I right? Then I can write Q is equal to sigma A. Okay. Am I right? One more. I can write E is equal to sigma by epsilon naught also in terms of electric field. Correct? E is equal to sigma by epsilon naught. Then I can write sigma is equal to E into epsilon naught. Am I right? See here. We know that capacitance of the capacitor is equal to C is equal to epsilon naught A by D. Correct? Then I can write E epsilon naught A divided by 2 epsilon naught A by D in the place of C. Correct? Sorry. Now, shall I erase what we have done? We know that U is equal to Q square by TC. We also know that sigma is equal to Q by A. Then I can write in the place of Q sigma into A. Okay. We know that E is equal to sigma by epsilon naught. So I can write sigma is equal to epsilon naught into E. Fine. We know that C is equal to epsilon naught A by D. Substitute it. We got it till here. Now cancel whichever is getting cancelled. So what is getting cancelled? Can you help me? U is equal to E square epsilon naught square A square into D divided by 2 epsilon naught A. 1 epsilon naught and this one will get cancelled. So the remaining is U is equal to E square epsilon naught AD divided by 2. We want expression for the energy stored per unit volume. For energy stored per unit volume means U by V. Now it is volume is equal to E square by epsilon naught AD divided by 2 into volume. V is equal to volume. Don't get confused with the V and potential difference. Okay, now I have written it as volume. We know that volume is nothing but area into distance. See here, AB I can write it as area into D. Then I can write E square epsilon naught A D divided by 2 A D. Therefore, energy stored per unit volume is equal to E square epsilon naught divided by 2. Energy stored per unit volume, the expression is half epsilon naught E square or E square epsilon naught by 2. Any difficulties? Just keep on substituting, you'll get. See, this derivation, what now I have done is not that important, but you should know this. That is energy expression for energy stored per unit volume for solving the problems. That is half E square epsilon naught or epsilon naught E square by 2. Understood? Any doubts? Any doubts? Further, we are going to solve some problems. Okay? Thank you.